the next few days. That being said, let's get right into it. So today's topic, as I wrote, is in blue again, Taylor and Maclaurin Series. And now let me highlight that these are very useful tools in the fields of math, science, engineering, and computational mathematics, differential equations. These are going to come up everywhere. So let's start with a quick review of power series. I think it's important enough that we review it quickly. Quick review of power series. Remember that we had f of x. And f of x was going to get represented by some a sub 0, this series, plus. So it's a power series in x plus a sub 2 x squared plus a sub 3 x cubed plus dot dot dot. Okay. And then we discovered that we can take the derivative term by term of this. And so a sub 0 would go to 0 because that's a constant. This one would just go to a sub 1 plus this one would go to 2. So I'm going over here. 2 times a sub 2 times x plus 3 times a sub 3 times x squared plus 4 times a sub 4 of x cubed, etc. The second derivative at x of this same power series, well, once again, the a goes away, so I'm just left with, this x goes away, so that becomes 2a2 plus this becomes a 6, 3 times 2, because I had this 3 here and I took this 2 down, so 3 times 2 times a sub 3 x, so the squared becomes a linear, and then plus 4 times 3 times a sub 4, and the x cubed becomes an x squared, and that will carry on and on and on like that. The third derivative, and I'm doing this, some of you may see the pattern, some of you maybe not, so I'm going to do it anyway. This is a constant, it goes away. 3 times 2 times a sub 3, and then here this 2 comes down, so that becomes 4 times 3 times 2 times a sub 4 times x to the first, plus, well, what would the next one be? Probably 5 times 4 times 3 times, let's see, 5 times 4 times 3 times 2 times a sub 5 x squared, like that. And we remember that the radius of convergence of this very basic one, radius of convergence, I'm going to kind of write it in a little funny, so it's not really the radius of convergence, but x has to be between -1 and 1. So if x works as in here, all these should hold true. All of the above should hold true at x equals 0. So I'm going to take a quick break here. So all of the above, all these equations up here should hold true at x equals 0, which means that f of 0 should really just equal a sub 0, because all these other terms have an x in them, so they all go away. And more interestingly, f prime of 0 should equal, well, just a sub 1. And then I could say f double prime of 0 equals only 2 times a sub 2 times a sub 2. And then I could go f triple prime of 0 equals, let's see, f triple prime, all this stuff goes away, 3 times 2 times a sub 3. Interesting. 3 times 2 times a sub 3. And it appears I'm developing a pattern where the nth derivative evaluated at 0 is sure going to look like n factorial. So page, you were wondering where the factorial comes from. There it is, times a sub n. Well, that's very, very useful to us, because if I wanted to go back and plug in what my a sub 0 and my a sub 1 are, this says a sub 0 is just f of 0. A sub 1 is just f prime of 0. This, to me, indicates that a sub 2 is f double prime at 0 over 2 factorial is a sub 2. And this says a sub 3. I know exactly what a sub 3 is. It's f triple prime at 0 divided by 3 factorial. And this says that a sub n equals the nth derivative at 0, all divided by n factorial. So if I put all that stuff to use up here, these coefficients, now that I've solved from all my a's, that's very useful, because I can stick this in here and I can say for some f of x that I don't necessarily know, I can estimate that, or maybe even say exactly what it is. It's f of 0 plus f prime of 0 times x plus f double prime at 0 over 2 factorial times x squared plus f triple prime at 0 over 3 factorial times x cubed plus, and the final plus, I'll put a dot 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 here, plus, and this is the most important one, f the nth derivative evaluated at 0 divided by n factorial times x to the nth power. So we have nth derivatives, nth powers, n factorial all coming together to help us represent this function in terms of just a sum of a bunch of products, right? And again, the reason this is so valuable in today's time is that a calculator is very good at multiplying and adding, right? It's not very good at strange transcendental functions, sines and cosines and hyperbolics and all this stuff, logarithms, right? But a calculator is very good at doing this kind of thing. So this thing is called a Taylor series. About x equals 0, because we're starting with, say, we're assuming that we know this stuff about 0, and then we're going off to find f of x, or we can call this Maclaurin series. Now it's kind of interesting because Taylor, I think his name was Brooke Taylor and Colin Maclaurin, lived about the same time. Maclaurin was a Scottish guy and Taylor was an English guy. This is in the days when Scotland and England didn't get along so well. And they lived about the same time, and Maclaurin came up with a special case where it's about 0. Taylor came up with another case, but they both got their own names on it. So if we were to look at a more general case, so the Maclaurin series, which is this one, is really useful if I know a lot of information, my values and my derivatives at 0. And I want to find a value of f of x that's close to 0. And the Taylor series comes in when I want to find a value of x that is somewhere close to some other letter a. So just like I shifted that power series in the last lecture, I can say that a more general case is that f of x equals some a sub 0 plus some a sub 1 times x minus a to the first plus a sub 2 times x minus a squared plus a sub 3 times x minus a cubed plus dot dot dot, right? Well, when I was trying to determine the coefficients, and I'm over on the left side here, when I was trying to come up with the coefficients for the Maclaurin series, well, I plugged in this really convenient value, x equals 0. Why did I do that? Because then when I go up here to my derivatives, all these other x terms go away because I used x equals 0, right? This is a tool we've used before. Now, over here back on the right side, what would be the convenient value of a to use, or excuse me, what would be the convenient value of x to use to make this go away and this go away and this go away? Well, sure, I would use x equals a. And that would lead to the coefficients that make this Taylor series look like this. And this is now a Taylor series, not a Maclaurin series. F of x would equal f of a. This is my first coefficient, which is analogous to this one over here, except now I'm doing f of a, plus f prime of a over 1 factorial times x minus a to the first, plus, and as you'd imagine, f double prime of a over 2 factorial times x minus a squared plus, I'll just put another plus down here, f triple prime at a over 3 factorial times x minus a to the cubed, and then my final, my general term would be f the nth derivative evaluated at my a divided by n factorial, and this will be times this term x minus a to the nth power. And that gives us a much more flexible series, because now if I know, some information about maybe the sign of 2 pi or the sign of 3 pi or something like that, then I can use 3 pi as kind of my home base, a, and I can find some values of x that are nearby to that. So this is what it is. We'll insert the definition of a Taylor and Maclaurin series. Right there it is. So it's the Taylor series is when we have x minus a, so it's more general. We know some value of a, and we're trying to find some x nearby. Right? We know a, we're trying to find the value of x that's nearby. The Maclaurin series, we know 0, and we're trying to find some value of x nearby. Now, why did these get 2 separate names? Probably just to honor both of these guys for coming up with it independently. But I don't know. I'd be curious if somebody could look that up and find out what the real story is. So that raises the question, can I find a Taylor series for any function? And the answer is usually. So let's look at a few steps to do that. Step one is to determine your center point. Now, remember the other day when we took this 1 over 1 minus x, but we shifted it, and so really we shifted it by a, so really what we're doing here is, in essence, your a in x minus a. Right. So let's say I know that the cosine of pi is -1, and so I want to. If I know that, I know all the derivatives at -1. I want to find some nearby, some things that are a little bit less than pi, a little bit more than pi. Then I'm going to pick pi as my a. Right. You'll see what that means in a little bit. 2. Find several derivatives. We're going to find several derivatives. So we'll find f of a, f prime of a, f double prime of a, and then hopefully we can find some pattern, and then we can find a nice clean formula for the nth derivative of a. So really this is going to become a series, or a sequence. This will become a sequence, and we want to find an explicit formula for the nth term of the sequence. Then what we do is write out the first few terms. So we need to write out our first few terms, or the first few coefficients is really what we're after. F of x is going to equal f of a plus f prime of a over 1 times x plus f double prime of a over 2 factorial times x squared plus, and hopefully we have a nice neat pattern for the nth derivative at a over n factorial times x to the nth. And this is really what we're after. And then we've got it. We've got our series figured out. But it's always good to check. Right. The nice thing about these is it's always pretty easy to check our answer. So let's do an example. And the example that I'm going to propose would be f of x equals 1 over x plus 2. And I'm going to say that it's centered at a equals 0. All right, so we'll pick a pretty easy case. I'm going to write this as f of x equals x plus 2 raised to the -1 power. That's going to make it easier for me to kind of come up with my derivatives, because that's easier to do the power rule and the quotient rule. So f prime of x equals, well, power comes out front, -1 times x plus 2 to the negative 2. All right. F double prime of x equals, well, the power comes out front again, negative 2 times negative 1 times x plus 2 to the negative 2, negative 3 this time. And then f triple prime equals negative 3 times negative 2 times negative 1 times x plus 2 to the negative 4. Right, and we can see this pattern here. And finally, pretty sure I can get an f sub n, or f to the nth derivative, equals. It's here I've got a negative, here negative times negative is positive, 3 of those is negative, so my 0th derivative, or my first derivative is negative. So I can say that it's negative 1 to the n, because they'll alternate like that. The 0th derivative, my original function, is positive, so 0, that becomes a positive 1. And then it's going to become, this just becomes, this is the third derivative, 3 times 2 times 1, so it becomes n factorial over x plus 2, which is my original thing, to the n plus 1 on the bottom. Right, because my first derivative, it's over to the negative 2. My second derivative, it's to the negative 3. And by putting it to the bottom, that kind of took care of the negative sign. All right, so this is my nth derivative. The next step is to write out the first few terms, right? But to get the first few terms, I need to go back and figure out what f of 0 is, f prime of 0, f double prime of 0, f triple prime of 0. I need to find all these things. So let's plug that in there and write in f of 0. Well, that just 0 plus 2 is 2, and so that's just 1/2. And then here I have a negative, and then 0 plus 2 is 2, so it's negative 1/4. And then my next one, it's negative, negative, positive 1/8, but I've got this 2 here, so it's going to be a positive 2/8. I'm going to leave it like that. You'll see why in a sec. The next one is negative, 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 so it's negative 16th, but I've got a 6, so it's negative 6/16, like that. So now when I write out these terms, my f of x is going to equal f of 0, which is 1/2, plus f prime of x plus 2, which becomes plus, I'm going to write it like this, negative 1/4 over 1 factorial, plus, that'll be a positive 2/8 this is times an x, plus a positive 2/8 over 2 factorial times x squared, plus the next one is a negative 6/16 over 3 factorial times x cubed, plus dot dot dot. Well, conveniently, and now for the first time this lecture I get to pull out the red pen, this 2 cancels out with this 2 factorial, and this negative 6 cancels out with this 3 factorial there. So I can see that my pattern is going to look like this. And so this equals 1/2 minus 1/4 over 1, so it's minus 1/4 x, plus the 2's cancel there, so I'm left with is a 1/8 x squared, minus, since the 6 is canceled, it's just a 1/16 x cubed. Right, so I can see that this is geometric, right? 1/2, negative 1/4. And my r equals negative 1/2 x. My first term is 1/2. So my sum, this equals, I'm going to write it up here. So this stuff leads me to believe it. Up here it goes to 1/2 over 1 minus 1/2 x, and that equals negative 1/2 x. And that means it's 1 over 2 plus x. Right, so I multiplied top and bottom by 2, so this became a 2. This became just an x, and this became just a 1. So 1 over 2 plus x, which is the same as my original 1 over x plus 2 that I was going for. All right, so this actually works. Now, 1 over x plus 2, that's not a terribly interesting function. So, we'll do some more interesting ones, but at this point, I'm afraid that I may be losing some of you. Does this make sense? Take 2. All right. I'm going to draw a picture, and that's my best straight line I can draw there, and then that's the best straight line I can draw there. And we're going to draw some function. I'm going to label my coordinates t and d, all right, for time and distance. You'll see why in a second again. And I'm going to say that my time versus distance plot looks something like this, right, like that. I'm going to call this my A. And I mean, I know something about A, but I don't know, but I would like to know something about X. So if I go up here, I can go up this way and go back this way. This becomes f of A. And then I go up here and I go back over here. This becomes f of x. All right. I know f of A. What is f of x? Okay, at first take, I could say, my first attempt, my first take. I just wrote take because it's easier to write than attempt. I could just write that f of x equals f of A. Right, and that's essentially saying that I've got this point here, and I'm just going to say it's the same. So this becomes my first attempt. Right. Well, I think we can make a better attempt than that, and I'm going to say that this is 1. My second take, which will be in blue, is that f of x equals f of A plus some rise. Well, rise, what do I mean by that? Well, I can remember that slope equals rise over run. And so that means that rise equals slope times run, or m times run, that's right. And so that really means that f of x equals f of a plus m times run, which really equals f of a plus m is my slope, which is f prime of a, and my run, right, how far am I going this way, is really x minus a. Oh, now that's interesting. That looks pretty familiar. Right, so if I say this is my a, and let's do that in a thin pen. So I can say that this is my slope times my run. So this is my second take, which is still not very good. Why is that not very good? I mean, it's better than the first one, but the problem is that the slope here is different than the slope here. I've got some curvature. So wouldn't it be interesting if I could account for my curvature? So let's change colors and change thicknesses and make it a third attempt. Third take. I'm going to say that f of x equals f of a, right, which is my first attempt, which was close. F of a plus f prime of a times x minus a. But now I have to count for the curvature, which I know is the second derivative, f double prime of a times x minus a squared. Yeah, so x minus a squared. Why did I do that? Well, if we go over here and we look at the units, and I'll do this in green because it continues to be kind of along the same time. Look at the units. And we'll say those are meters and seconds. We said that meters equals, what do we say? It's f of a, which I know is in meters, plus my m, which is slope, which is really meters per second, the change in distance, which is meters, over the change in time, which is seconds. So this becomes meters per second times my run, which was seconds, which equals meters again. So the units work out. Well, for our third take, which we went back in green, I want meters equals meters, which was just my original f of a, plus meters per second times second, plus, if I take the second derivative, the change in, so I'm looking at the change in meters per second for the per change in time, right? That becomes meters per second squared. Meters per second per second. Well, to get my units to work out, I've got to multiply that by seconds squared. So that is why I have to add this second squared, because the second derivative, it's going to be units of 1 over something squared, and this has got to be something squared to make up for that. For the physics students, hopefully that makes sense. If you have not taken physics, maybe that wasn't so helpful. So let's say I want to find the Taylor series for something more interesting. So find Taylor series. And what is a Taylor series again? It's a polynomial, right? It's a power series, x squared, x cubed, x to the fourth. Taylor series for, let's say, f of x equals the cosine of x. And then my step one is to find, and this is around the point x equals 0. So we're going to just kind of work around the origin again. my first step is to write out a few points. So I'm going to say that f of 0 equals the cosine of 0 equals 1. And my f prime of 0 equals the derivative of cosine is negative sine of 0, which equals the sine of 0 is 0, so that remains 0. That's nice. The second derivative, f double prime of 0, equals derivative of negative sine is negative cosine of 0 equals negative 1. And the triple prime of 0, derivative of negative cosine is, I think, positive sine, right? Positive sine of 0. Well, the sine of 0 is still 0, so that remains 0. The fourth derivative, evaluated at 0, equals derivative of sine is cosine. So right back to where we started, and that equals 1. So it goes 1, 0, negative 1, 0, 1, 0, negative 1, 0. It kind of alternates like that. Now this alternating every other thing, is going to be a little tricky. So basically what I'm going to suggest is that we just neglect these. So we're really only interested in the even terms. So what I'm going to suggest we do is just we say that f of 2n, right? So I'm going to go every other one of 0 equals negative 1 to the n. All right, does that make sense? 1, negative 1, 1, so we just do the even ones. If we start at 0, so the 0th derivative just becomes negative 1 to the 0, which is 1. That works. N goes up to 1, but then my derivative goes up to the second derivative. So I skip straight from here to here with n equals 1. So it becomes the second derivative equals negative 1 to the n, which is negative 1, which works out to be negative 1. And then I'm going to skip straight to here. When n equals 2, I skip straight to the fourth derivative. F fourth derivative of 0 equals negative 1 to the 2, which is positive 1, which is 1. So that works out there. So I remember when I write out these terms, I want to write out that the cosine of x is going to equal something plus something times x to the first plus something times x to the second plus something times x to the third. Now, here I have to recognize that what do I multiply by x to the first? It's my first derivative. What do I multiply by x to the third? It's my third derivative. And these odd derivatives are all 0. My odd derivatives are all 0. So when I write this out, I'm just going to write out my even derivatives. And the 0th derivative really is an even derivative, so that's my first one, so that's just going to be 1. And I'm going to say plus, my second derivative gives me a negative 1, but I'm going to divide that by 2 factorial, so it's negative 1 over 2 factorial times x squared. Plus, now my third derivative is going to be a sine, which is 0, so that goes away. So my fourth derivative is a positive 1 over 4 factorial times x to the fourth. Plus, my third derivative, or my fifth derivative, would be a sine, which is 0, so that goes away. So the next one is going to be a negative 1 over 6 factorial times x to the sixth. And finally, that comes out to plus a negative 1. I'm going to alternate this with n. But my powers of x go up by 2's, so that's 2n. And my factorials also go up by 2's, so that's 2n factorial. So that's my cosine. So I can finally write over here that cosine of x equals the sum from n equals 0 to infinity of negative 1 to the n power x to the 2n power over 2n factorial. Like that. Now it's interesting to note that my powers of x are all even. And they're even. Now let's look at what cosine looks like. If I draw a quick plot of cosine, it starts here and it goes down, it goes up, and then it goes down, and then this side it goes down and up. So this is symmetric about the y-axis here. So this is a cosine really is an even function. An even function. And composed of even powers. So let's maybe I'll try to highlight that in green. So maybe I'll highlight it in yellow. I can't use yellow. So here we have this even function. And here we have these even powers. So that turns out to be pretty cool. Okay, so here we're back with a really slick Mathematica demo of how Taylor series work. And I'm going to kind of duplicate the example we just did, where I'm trying to evaluate the cosine of x with a Taylor series. Or what really is a Taylor polynomial, and the approximation order is the 0th one. And I'm doing it about the point x equals 0. And so the cosine of 0 is 1. So my first approximation, my 0th order approximation is just that cosine of x equals 1, right? Which we know is not true. It just goes 1 both directions. So that's a pretty bad approximation. And then what I can do is increment this up by 1. And notice nothing changed. Now I got a little tip in my line here. That's because of some numerical rounding errors there. But essentially it's the same. Why is that? Because cosine is an even function, and I only really included my second powers. So it's no surprise that this didn't do anything. Now what's the next term going to be? It's going to have to do with x squared, and it's going to be negative. So we can expect an upside down parabola. And sure enough, there it is. So now we have an upside down parabola because we've got this negative x squared. Now, do you think if I step this up to the third order, so the third level Taylor polynomial, x cubed, is that going to change anything? Probably not, because that the derivative, the third derivative, is a 0, and sure enough, it doesn't do anything. The next one will be a fourth order, so it'll go up, and down. Let's take a look. Sure enough, now we're starting to approximate this, and I can quickly go through these, and we can see that as I increase, these even powers, it gets closer and closer, except I limit this at 10, or 11, so I should really change that in the code. But I can override it here. I can go up to the, let's say, the 14th power and see how that does for me. Now look at this. I've got a really good approximation out here. It just starts to stray here. So everywhere from, say, negative pi to pi, it does a pretty good job of approximating this. I can take it out to this, say, the 20th approximation. And that pretty much nails it over, from negative 2 pi all the way to positive 2 pi. So that's pretty good. Now, I talked about, the centering point. And so I'm going to slide this all the way back to here. And I can move the centering point. Say I want to take my Taylor polynomial about this point. And then sure enough, cosine of negative pi over 2 is 0. And so my estimate is 0. And as I increase my polynomial here, the first one is 1. So now it's 1x, and I keep going up like that. And as I increase the polynomials, this time the odd ones matter. Why? It's because my even derivatives are 0, and it's my odd derivatives that have a value, because I'm starting at a different point. I'm starting at pi over 2, negative pi over 2 in this case. And so I can continue going forward with this demo, and I can see I can get better and better, but my radius of convergence really is no longer centered at 0. My radius of convergence, my interval of convergence, is centered about this my center point, my A, which in this case is negative pi over 2. And so I can keep increasing these, and it gets to be a better and better approximation. All right. The same thing goes for sine. I can do the same thing with sine, about x equals 0, slide this all the way back over here. And, at first this is just a horizontal line. Why? Because f of 0 is 0. But as soon as I add a first order approximation, I get this line, which matches at least the slope and the value. And now I start to match curvature, and the same thing happens as I increase these polynomial orders. So I'm going all the way up to the 11th power now. I really get a pretty good approximation all along here. This is available if you just Google Wolfram Demonstration Project or Mathematica Taylor Series. You can find this. It's all free. You can download it for yourself. Okay, so hopefully that Mathematica demo showed you, if not convinced you, that we really can represent something, a function like cosine, which we call a transcendental function, a trigonometric function, with a polynomial, right? Polynomials we studied back in 8th grade, maybe 9th grade, but we can use a polynomial to approximate a cosine function. Now, if you recall back from the lecture the other day, if you watched that, I came up with some kind of funny power series, and my power series looked like this. I said it's f of x equals 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial. I know this is getting long, but I think this is pretty cool. And then I said, well, let's do, we did this term-by-term derivation, or term-by-term differentiation. And so we said, what's f prime of x? Well, the 1 goes to 0, the x just becomes a 1. And the x squared over 2 becomes 2x over 2 factorial, but the 2's cancel, so we're just left with x over 1 factorial. And the x cubed over 3, 3x squared, 3's cancel, this becomes x squared over 2 factorial, plus the x fourth becomes 3x cubed, or 4x cubed, the 4's cancel, so that becomes x cubed over 3 factorial, plus x to the 4th over 4 factorial. Now it's important to remember that I actually did take a derivative here, and I'll do this in kind of light blue, that this thing turned into this, and this thing turned into this, and this thing turned into that, and that thing turned into that, and that thing turned into that. All right. And so if I go through and I take the second derivative, well, same deal here. This will become 1 plus x over 1 factorial plus, you can see that I was going to make an x there. I covered that up. This one becomes x squared over 2 factorial plus x cubed over 3 factorial plus, and this will become, well, the next one, but I didn't draw it in there. So let's again look at what happened. This turned into that, that turned into that, that turned into that, and that turned into that. And we can see this is going to keep happening over and over and over again. So I can write that f of x is the same as the first derivative of x equals the same as the second derivative. So there's only one thing that this could be, and that's the exponential function, e to the x. Which I think is just really, really amazing that this is convincing to me that we keep taking the derivative over and over again. It's the same. So the only function that does that is e to the x. So this polynomial has got to be e to the x. So that's an interesting approach to that one. Finally, and this is the last example, I promise. We did an exponential function. We did a trig function. What about another trig function? The tangent of x. Right? Well, I know that the tangent equals sine of x over cosine of x, and hopefully you guys all know that by now too. I really hope you do. And so the sine of x, we didn't talk about the sine of x, but remember that the cosine, well, let's do the cosine first. The cosine turned out to it's an even function, so it's the even power, so it was 1 plus x, oops, it was actually 1 minus. Now, I will give you the basic trig functions on the exam, but I hope that after working with these a little bit, they become obvious. So it's 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus ... The sine function, on the other hand, is an odd function. Well, what's the easiest odd function we know? That's x. Minus, another odd function we know, x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 6th over, nope, I got carried away there. I was cheating by looking down below, and I got busted cheating. 7 factorial plus ... Right? Now, this is a hassle. The way to approach this one is in thick black ink. And we want to take the sine function, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and divide it by, yep, you knew it was coming, the cosine function, which is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus ... Okay. All right, well, how do we do this? And if you notice, this is actually the first problem on your homework assignment. I'm going to give you a shove in the right direction because many of you probably haven't done polynomial long division in a long time. How many times does 1 go into x? It goes into x times. So what's x times 1 is x. X times negative x squared over 2 factorial is x cubed minus x cubed over 2 factorial. And then x times x to the 4th over 4 factorial is plus x to the 5th over 4 factorial. And that's all I've got for now. Now what do? I have to subtract these things, right? I subtract this. X minus x is 0. That's nice. Now, how do I subtract these? My denominators are factorials. Here's where your knowledge of factorials is going to be important, and I'm going to go to a thin pen because this gets tricky. I want my common denominator to be 3 factorial. So really this is just 3 times 2 factorial, and so that means I got to put a 3x cubed up there. Over here, common denominator is going to be 5 factorial, which is really just 5 times 4 factorial, which means I have to put a 5 up here. And I can go back to my fat marker and say, so this is x cubed minus a negative 3x cubed, which is really plus 3x cubed. So that gives me 2x cubed over 3 factorial. And then this minus this is going to be a minus x to the 5th minus 5x to the 5th is 4x to the 5th over, well, 5 factorials make common denominator. And then I have to bring this down. This minus nothing gives me a minus x to the 7th over 7 factorial. How many times does 1 go into this thing? Well, it goes in positive 2x cubed over 3 factorial times plus 2x cubed over 3 factorial. I multiply this. What is this times 1? Well, it's 2x cubed over 3 factorial. And then what is this times this? Well, let's see, it's 2x cubed times x squared, which will be negative 2x to the 5th, minus 2x to the 5th, over, holy cow, 3 factorial times 2 factorial. Well, I'll just write that as 3 factorial times 2 factorial. And then this times this gives me a positive 2x to the 7th over 3 factorial times 4 factorial. And then, again, we have to subtract this. And you have to do that. So I think the homework asks you to get it out to 4 or 5 terms. And you can see why I only assigned, I think, 45 every other odd, so something like 11 problems. They're not all this lengthy, but it's a good exercise to go through. This needs to be fresh. Okay, you got to remember how to do this stuff. The reason we taught you this for a reason back in 10th grade. Now it's time to use it. So that's it on Taylor Series. Please go through this lecture. Please take a look at the homework, and we will answer any questions you have then in class. See you later.